Hey everyone, how are we doing? The homework is due on the 12th. Oh my gosh. That is next Tuesday. So I was like, let's start working on it. My hair's all crazy. Start working on it here. Sure, it's disappearing. That's the way it goes. What is this? Did they change it? They changed the way this looked? Oh my gosh. I think they changed or updated something. Let me see this again. I'm gonna go to preview. You'll see it here in a moment, but I think they changed something major about my Pearson. So replace questions again. Oh, there we go. It's different if I go there. So it's always different. Oh, it is different. Wow. Okay, it looks like this now. So it shows the questions over here. And let me get MuBot going. We're starting early. I have a meeting today. So I was like, we'll start early and then I can do this. Let's wake up MuBot. Go down here. Hello, MuBot. There's MuBot. Yes, we want to wake up MuBot. And there's the first question. Is it going to open? What in the world? I don't know if I like that. Huh. That's interesting. That's weird. That just got updated. Wow. That's a whole new thing over here. I wish it showed like, that should have like a 1 on it, like the 1 in the circle or something, but that's new. That's different. There's MuBot over here. MuBot is awake. Let's throw out some points. No one's here, but okay, there we go. MuBot is awake in the background. We now got this thing to contend with over on the side that just hangs out there. Takes up part of the screen. It's very, very important. Very, very important. And we've got questions. So let's mark this in the chat. And people can check this out later because I don't know if anyone's here right now. So we will put this in the chat. We've got here 3:13, Stat 201, chapter, what are we doing? Chapter 13. Chapter 13 homework, question 1. Okay, let's check this out. So the first question right here is about confidence intervals. And when you're doing confidence intervals, you have to know the notation. So if you haven't done this, I would suggest making a spot in your notebook for notation and then just write down. Usually the back of your notebook's really good for that, but print out all the notation, memorize it all. So that way when you see something, you know it. What do I mean by that? Well, when we look at this question, we need to know the notation to solve it, as Leo always says.
Notation, brother.
This one right there. So we start highlighting things in this question that might lead to notation. And you see these things right here. Noel, good to see you. Yes. Because I have a meeting today, I'm starting early and I'm going over the full homework right now. So open up the homework, check it out, and we'll get it done. Thank you, Noel, for being here. Let's throw you some big MuBot points. Good to see you. So the notation for this is our sample size, which is lowercase n. Capital N is population size, or sometimes used for normally distributed. It's used in 2 spots in statistics. Now we have over here, 45% of them reported that they are online several times a day. So that is the sample proportion, but then we can do Q hat equals 1 minus P hat, which is the complement of the sample proportion. So P hat and Q hat are complements, and there is Q hat. So Q hat is going to be 0.55, and I'm blocking it slightly right there. Now, these are the lower bound and the upper bound, as in I am 95% confident that the true proportion of people who are online constantly for whoever they're talking about here, teenagers 13 to 17 years old, are contained in the interval 42 to 48%. And MuBot's also putting the interpretation for confidence intervals in the chat right now. You can see I just used it right here. I am 95% confident that the true proportion of teenagers who are online constantly is contained in the interval 42 to 48%. A lot of people get stuck on the middle part because they don't know how to say what true thing they're talking about, but we're trying to analyze the proportion of teenagers who are online constantly. So the true proportion of teenagers who is online constantly is what we're trying to understand from the sample proportion. And lastly, we have 95% confidence, which relates to the z-score of 1.96. The reason that is because the middle 95% of the curve is contained between a z-score of negative 1.96 and positive 1.96, so right about there-ish. Negative 1.96 and positive 1.96. It's basically 2, which we learned with the empirical rule early on, 95% confidence. And you can also go to the applet to get these numbers. We would give them to you on a test, but you should have a basic understanding of 95% confidence intervals is basically 2. On a test, it would say use 1.96 because we don't expect you to memorize the numbers as I've drawn right here. You would go to between, and there is 1.96, positive and negative version. So that's how we know 1.96 for 95% confidence, or for 90% confidence, 1.6445 or 1.6449 if we go even further decimals, because you can carry all your decimals. There you go. It's actually 485. So we usually round to 2, sometimes 3 decimals when doing the z-score for a confidence interval. So once again, we stated you have to know the notation, because from here, the problems get easier to solve. So take a moment, write down the notation. P hat is the true proportion. Z is going to be the z-score used to dictate the percent confidence for an interval. Lower and upper bound are the lower estimate and upper estimate, such as like, I'm going to go to a restaurant tonight. I'm not actually going to one, but I believe the steak should cost between $20 to $30. 20 to 30, lower to upper bound. It doesn't mean the truth will be in that interval. There's my meeting. It doesn't mean the truth will be in that interval. It means we are 95% confident the truth is contained in that interval. The sample size is how many people were spoke to, which is lowercase n. I believe that's everything on the screen right here in terms of notation. So now let's look at the problem and what do they want us to do? So all they really want us to do so far, and might be it, is just interpret the interval. So remember I said I am blank percent confident. So Noel, do you know which one it is? Think about which one sounds most like I am blank percent confident that the true blank is contained in the interval blank to blank. So you can read their interpretations, but try doing it yourself to say I am 95% confident that the true proportion of teenagers who are online constantly is contained in the interval 42 to 48%, or online several times a day. I am 95% confident that the true proportion of teenagers who are online constantly is contained in the interval 42 to 48%. So which of these, A, B, or C? Which of these, A, B, or C? So A is pretty good. I think it's B. Let's see here. I am 95% confident. Ooh, wait a minute. You might be right, Noel. Noel got 30 some points. Yes, it's not of the teenagers polled. It is A. You are correct, Noel, because B is talking about the sample. We know the truth for the sample. So you're right. This one says of the sample, we know the sample is 45%. We're trying to figure out the truth for all, which is if you asked all teenagers. Great job, Noel. I had read part of it. I had narrowed it down between A and B. So this is the sort of I am right there when I say I am. We don't usually talk like this about intervals, so good job. Next one says, I'm not selecting C, but I have accent right now. What does 95% confidence means? This goes to the law of large numbers. I'll say this answer right here. The law of large numbers states that over repeated trials, we would see 95% of 95% confidence intervals contain the truth. It's not that one interval contains the truth. It's to say, like, if you were to buy lottery tickets, the lottery ticket's either a winner or a loser, but your ticket has a 95% chance of being a winner. So over repeated trials, lottery tickets that have a 95% chance of winning, 95% of them would win. So over repeated trials, 95% confidence intervals contain the truth 95% of the time. So 95% of 95% confidence intervals contain the truth 95% of the time. I hope that makes sense. It makes sense to me. It's not that one has a 95% chance, because the lottery ticket, I'm equating it to a lottery ticket, is either a winner or a loser. But if you were to repeatedly buy the lottery tickets that have a 95% chance, 95% of those tickets would win over the long run, law of large numbers. So there is, if one collected many random samples, about 95% of the confidence intervals one constructs would contain the true proportion of teenagers who admit to being online several times a day. What does this one say? What's the difference? Of the sample size. That's a little bit pedantic to say that you have to do it of the sample size. It's just, sure, in this context, we did a sample size of this. 95% confidence intervals, you make a whole bunch of them, 95% of them contain the truth 95% of the time. They're really being very pedantic with that right there, so sure. Okay, next question. You know we're going to do some notation.
Notation.
All about that notation. This one's super duper easy, though. I'm basically going to write the thing on here and then say the answer. But remember, the best way to do these questions is to not select the answers or to not view them. If you know the answer without selecting it, you know the answer a lot better. So I'm not going to tell you right away. I want you to think through this and let's find it. Reaching out to standard errors. We actually call it standard errors now. It's found by p hat times q hat over n square root. Makes us blank percent confident that the true proportion is contained in the interval. So Noel, we kind of mentioned this a second ago. If we reach out to standard errors, how confident are we? Hints on the screen. So when you look at this right here, a confidence interval for the true proportion, so which one? You're right. 68, 95, 99.7, going 1, 2, 3. So p hat plus or minus z star p hat times q hat over n square root. So the standard error is known as this quantity right here. Standard error is based on a sample. Standard deviation would be p times q over n square root. This portion right here is called the margin of error, which is the plus or minus on any sort of interval we create. So if you change the z, then you'd be reaching out 2. The technical answer is, well, so which answer do you think it is, Noel? Is it 68, 95, or 99.7 when you go out 2 standard errors? Yes, you're right. And it's actually 95 point, is it 95.449 too? I don't think it, 95, I think it's 95.45. But let me see right here. When you reach out 2, we can go to the applet. Mubot's got the applet in the chat. So when you reach out 2, so if we go to find using x, we go to between -2 and +2, 95.449. There it is, 95.449. That is when you reach out 2. But the technical answer is 1.96, and 1.96 is basically, it's actually 1.95996. It's 1.96. Every other statistician in the world is going to tell you it's 1.96. If you just go to a few decimals and you do 1.96, you're fine. Every statistician out there. But the technical answer is 1.95996. But don't do that. Someone's gonna. I did that on a test and actually lost points in college. I rolled 1.95996 and they said it's 1.96, and I said, but I just carried the extra decimals. They said, why do you know that? I said, I don't know. But you can see this is basically 2. So a lot of times if you're doing it in your head, you just use 2 basically, but then computers and calculators will use 1.96 or 1.95996. And if you go more exact, what I'm saying here is there's always decimals to carry that we don't carry. Like I say 1.96 or 1.95996, and there it is. And then there's 3985, which I doubt I'll remember. So the answer to this question is, if you reach out 2 standard errors, you've basically made a 95% confidence interval, which it said basically, and you're basically making a 95. There we go. Basically 95. So it's not from a formula. It's because the normal curve has contained within 1.96 standard deviations or standard errors, whichever we're doing using a standard deviation or standard error, contains 95% of the information. So even if you're doing it for like like means or things like that, always 1.96 will contain 1.96. We'll bring it back to that. 1.96 standard deviations will contain 95% of the area. There's nothing, it's just the question itself will say make a 95% confidence interval. You say, oh, 1.96. Or the question might say make a 90% confidence interval. So what would be the z-score there, Noel? So you have to go to this page. If the question said to you make a 90% confidence interval, what would be the z-score? So if the question said make a 90% confidence interval, what would be the z-score? Like when you solve your formula, what would you enter into the z-score on the formula if it said, so you have to go to the z-score here, which is dictated by the percent confidence. So the z-score right there is dictated by how confident you are. So when it says 95% confident, use 1.96. If it said 90% confident, what would you use? So whatever confidence level it is, and that's why we put a star on it usually to say dictated by level of confidence. So if it said you are 90% confident, what z-score would you use? So you have to go to the applet. And on the applet, you have to click between, and then you have to enter in 90% confidence. So what would be your z-score if it said you're 90% confident? It has nothing to do really with p hat. P hat is part of the formula, but p hat doesn't go into the calculation from it. Yeah, do it. Check it out. Do it. And so how do we know what the z-score is? The confidence interval dictates a level of confidence. That is then used to find the z-score. So the z-score is always figured out by, I'm this percent confident. Let me go find the z-score relative to that, which covers that amount of the middle of the curve. So give it a shot. So you might have, so 90 right here, you need to have 90 in between. You might have 99. That is a 99% confidence interval. 2.5758 is 99% confidence. So you might have hit an extra 9 right there. 2.5758 is 99, or rounded 2 decimals, 2.58. That is 99% confident. But going to 90% confident is 1.645. They stay the same, and technically I would carry a few more decimals. Oh, wait a minute. Oh, that's why I was like, what's going on right there? 1.645. Yeah, there you go. And good work. Yeah, this is how you use the applet. Points for you, Noel, right there. Because now this is the z-score relative to a 90% confidence interval. So 2.5758 or 2.3263 is a 98%. They don't change. So that's why I've memorized 2.3263. So they don't change. So every semester when I do these, I see the same z-scores. I'm like, well, 98% confidence is 2.3263. Notice how if you go from 90, it's smaller, and if you go to 95, it gets wider. If you go to 98, it keeps getting wider. So the more confident you are, the more wider the interval, because the z-score, which is part of the margin of error, is multiplied. This question has you just find the margin of error. Let's mark it in the notes. And we just have to solve the margin of error part of the formula. We might have just enough time to do the full homework. We might have just enough time. Let's see. Where is the margin of error in the formula to calculate the confidence interval? So you need to know, a learning objective here is where is the margin of error? So think of learning objectives, and you should be able to answer this pretty quickly. When you do your formula, where is the margin of error? It's everything where. So the margin of error is everything where. No. Well, darn. It's going to block it. Wait. Oh, there we go. Perfect. The margin of error is where? You can see it. I've drawn it out right here. Where is the margin of error? Well, so tell me and let me know what you're confused on. So the margin of error is everything in the formula after the plus or minus. When you hear margin of error, everything after the plus or minus. The margin of error has how confident you are based on the z-score. It also has the standard error of what you're calculating, which is a metric of variation to show you kind of how spread out it is. So it's basically a standard deviation. Like standard error, we call it that because it's based on an estimate. Well, don't worry about the numbers yet. Just a big learning objective right now is, what is the margin of error? The margin of error in an interval is everything after the plus or minus. So if it asks us to calculate the margin of error, what I'm going to do is I'm going to delete everything here because we're only calculating this quantity. Does that make sense, Noel, right there? Because the question says, what is the margin of error? So it's just asking, what's this value right here? So the first objective is, once again, to think about what we need to know to solve these. What is the margin of error? It's a plus or minus on an interval. Well, here's the plus or minus on the formula. So we're going to ignore the rest of the formula and only focus in on calculating the margin of error. So first off, we have to find how confident we are. First, it says 99% confident. So Noel, what is the z-score for that? You told me a second ago. What is the z-score for that? 99% confident. I'll find the other part of it because now we have to go up here and we have to do p hat and q hat. So what is the z-score relative to that? P hat 0.747, q hat. Double check. That's, remember, 99% confident. The first one you gave me, 99% confident. And this is n right here. 99% confident. So at 99% confident is a z of 2.5758. I carry out the extra decimal on it. And the way we get that, check out the applet that MuBot's been saying in the chat, is you go here and do go between, make sure you've selected find x using p-value and input the area right there. Make sure you have the standard normal, and there it is, 2.5758 is containing the middle 99% of the data. So that is a 99% confidence interval. And now we just plug in the numbers. So if you notice, we've solved out all the numbers right here. We plug in 2.5758 square root 0.747 times 0. My gosh. Okay, let me do it down low here because my handwriting is not that good to write that small, even though I got a really cool pen and everything. So, come on. 0.747 square root times 0.253 over 1997, 2.5758. And once again, this is p hat times q hat over n square root. And you can see my work right here where I identified p hat, q hat, n is 1997, and 2.5758 from the applet. So from here, it's really just solving this equation. All you do first is you solve out the standard error. To solve the standard error, you do 0.747 and times that by 2.53, divide by 1997, and then you square root the whole quantity. Do not do over n square root, and this is the standard error. Now, if you notice, this is about 1%, so we're going to get about, very close to this, we're going to get about 2.5% or 0.025. So we could probably guess that, but let's do a quick guess. 0.025. Check answer. We got it. And it's just the numbers were really nice because this is the standard error. This is going to get multiplied by that 2.5758. So solve the inner part of the equation. I've already square rooted it, as you can see, times by 2.5758. And there it is right there. It does come out to that. So we could have carried more decimals, but the exact answer is currently on the screen. And just make sure to solve the math and you'll get it right there. So there's the exact answer and there's our answer right there. And it did round to 3 decimals. Nice and neat. So we put in the applet whatever the confidence is. Yes, you put into the applet your level of confidence. I am 99% confidence. That gives you the z-score. That gives you the z-score right here. So then the z-score is then used in the equation right there because the z-score is relative to the level of confidence. And look at the color coding right here, where the z-score dictates how confident we are, or rather how confident we are dictates the z-score. So when I say I'm 99% confident, the relative z-score is 2.5758 because it covers 99% of the middle of the curve. So p hat and q hat are independent, so is n of what z is. So good questions right there. Thank you, Noel. And now we have to interpret the interval. Once again, I am 99% confident that the true proportion of people who think the country's on the wrong track is contained within the interval. Then they don't even do it. Oh my God. I am 99% confident that the... Man, I don't like this interpretation. I don't like that interpretation. So we've never asked a test question like this. It's that the truth, is it whichever first is the P? Technically, either could be P or P hat or Q hat. So P hat and Q hat because they come from samples. It's kind of, it's a choice, remember? And in your project, you get to pick which one you want to be a success. So it's kind of a choice, whichever one you want to be P hat or Q hat. P hat is just usually the one of interest. Like if we have like the country's on the right track or the wrong track. If you say I'm interested in being on the right track proportion would be P hat. If you're interested in wrong track proportion is P hat. So it's kind of arbitrary which one is P hat and Q hat because they're just complements of each other. And then P hat means usually the success case and Q hat means the failure case. So if you're having people buy a product, usually you would say the proportion of people who buy because you're interested in people buying a product. So there's some context where we would mostly agree on what P and Q are, where P is going to be the probability of the success case and P is the true probability. Usually in a lot of statistics, we only know the sample, which is P hat, which is the sample probability of the success case of what we saw in a sample, to be redundant. Good questions, Noel. Good questions. I like it. Now we have compute the 95% confidence interval. Noel, this all boils down to what? This question right here is simply a what question. I've stated this a lot today, that this question is going to be merely a what question. Like, this question just 100% boils down to doing this. 100%. All this question boils down to is this. What's this question boil down to? I'll start it up right here and I'll show you. This question boils down to the following. My square root. Confidence level relative to this. Because you pick this based on the confidence. And then we have Voila, blue. It all boils down to notation. This is going to be 1.645. And this is n. This is p hat. If p hat is 0.517, q hat is 1 minus p hat. Q hat is equal to 0.483. There we go. Finding the z and plugging it in. Yep. So the z, we once again go to the applet over here. and we plug in 90% confident and get 1.645. A little nicer when we do that. Great job, Noel. Yes, exactly. Yep. And then we simply plug into the formula. So now we plug in 1 point, and you can carry more decimals. It never hurts to carry more decimals. 1.645 square root. Great job, Noel. Because the z-score is picked based on how confident you are. And we're going to use this as p hat. It's the one given. And then over square root, or over 4, 5. You might have just enough time to get the assignment done. I'm hoping I can get it done because I've got 10 minutes. So now we solve the standard error. The standard error is going to be, I'm just going to keep the standard error on the screen right here. 0.3 divided by 4.7. I think I hope I didn't miss hit a button. I can do it. Thank you, Noel. 0.00742 times 1.645 plus or minus 0.517. Everyone says my zeros look like sixes. My handwriting is not good. I literally grew up with computers my whole life, and that's why I can type fast, and I can't write. I can't write. It's sad. 0.0122. And then we do the plus or minus on that. So 0.517 plus this. So 53 or 5292. That's the upper bound because I added it. So this number plus this. Now we do this number minus this. So there we go. 5047 or 48. There we go. Correct. Yes, that is what we found. So this right here turned into that. Exactly. P times Q, or P hat times Q hat over N square root. Great job, Noel. That is what we had within the square root. So there we go. 525, 5292, 5292, 5292. All right, keep it in my head. That was 98. I'm seeing 98. Oh no, I lost it. Let's see. How many decimals? 1 decimal. Yay! I remembered it. I am 90% confident that the true proportion of people who plan to move from California is contained in the interval. Right here. Remember, try to write this on your own. I am 90% confident that the true proportion of people who plan to move from California is contained in the interval 50.4 to 52.9. So if the housing costs are too high, they're going to do an initiative. So the interval is completely above 50%. So the interval is greater than 50%, and the state is going to do the initiative. They should do it because a lot of people are moving, so they're going to do the initiative. It's got it. Oh, I don't know if we can do it. I don't know. If they're short questions, we can get it done. Oh, can we do it? Okay. Which of the following correctly interprets a 95% confidential? 95% of intervals contain the truth 95% of the time. 95% of samples will produce intervals that capture the true proportion, because that's what we're trying to find. Is we're trying, there it says about 95% of confidentials contain the truth, which means 5% of the intervals will not contain the truth. Law of large numbers. So easy one. This question's, we're not gonna be able to do this one. This is okay. We'll do 7 here. That one, we can get almost all of them done. Almost all. So I don't want to go too quick, because I don't want to have you not learning. This one is a true-false one, which is a little tricky. So I wish they just wrote higher confidence means smaller margin of error. So if you see here, as I increase the confidence, the interval gets wider. So that's false, because the z-score gets bigger. Higher confidence means larger margin of error, and then you break the app. Lower confidence means smaller margin of error. We need to go between for a confidence interval. So lower confidence means lower margin of error. So that is objectively false. Don't do that. True should be at the top. For a specified confidence interval, larger samples provide smaller margins of errors. This is true. Because when you look at the interval right here, the margin of error is the plus or minus. So when you have a larger sample is the n right there. and you'd be dividing by a larger number, making the interval smaller by making the standard error smaller. So a larger sample makes the interval smaller, and just think theoretically, if you take a larger sample, you'd have a better estimate of the truth as in a tighter interval. So you would, this is objectively true, have a smaller interval with a larger sample size. This one is tricky. For a fixed margin of errors, larger samples provide greater confidence. So this is saying that if you have a fixed margin of error, so this is the margin of error, and the margin of error is fixed at something like 0.04. So if you have a larger sample, then this is going to make this smaller. So to counterbalance that, you would need to go to the z-score and increase it to increase this, because the 0.04 is staying fixed. It's kind of a weird question. I don't love it. No test question technically does it. But if n were to increase, the margin of error would get smaller. But since we're keeping 0.04 fixed, you can counterbalance that by increasing the z. Exactly. Because increasing z makes the interval wider, increasing n makes the interval smaller. So if margin of error has to stay the same on the other side of the equation, if you increase n, so it's saying for a larger sample size, they provide greater confidence. That's true because larger sample size. If you want to counterbalance that, then increasing z makes the interval wider because increasing n makes the interval smaller. So this is a true statement. For a fixed margin of error, larger samples provide greater confidence. Don't love it. For a given confidence level, having the margin of error requires square rooting, requires sample size twice as large. So this one's a really great one. I do like this one a lot theoretically, because when you look at the margin of error right here, we'll go back in time a little bit. I might have time for one last one. So it's saying if you take 1/2 of this right here, that you could do this and just get 1/2 the amount and just do this right here. Problem is you can't just put 2 right there. You'd have to do you'd have to have square root of 2. But square root of 2, you'd have to have 2 in there where it can be 2, which is actually technically 1/4 square root. And why 1/4 square root? Because you need to figure out how much more of the sample size you need to do to get half the margin of error. And if you square root 1/2 or 1/4, my gosh, I cannot speak today, you get a half. And because of this, we can now include this in the radical right here via the rules of mathematics, and you'd get 4. So it doesn't require twice the sample size, it requires 4 times the sample size. It's the way exponential numbers work within sample sizes. So this statement is false. It would require 4 times the sample size. Then we got another one right here. I don't know. Can I speedrun this? I got 2 minutes. I have that out. I am 95% confident that the true proportion of cars made in Japan is contained in this interval. Do we meet the conditions? Oh, this is red snappers. Oh, we did this last time too, though. Okay, well, that's got it, Noel. I wasn't able to do the full thing. So we do meet the conditions here, I think. Yes, meet the conditions. No, we don't. Wait, yes, we meet them. Don't wait too quick. I can't. 95% confidence roll. But there we go. Check interval. How close was I? Kind of close. No office hours at 10 today. I'll head off. Got office hours. Bye for now, everyone. Bye.